are discussing strain rate in fluid mechanics, and we have discussed these topics. We started distinguishing fluids from solids and found that deformation is for solids and rate of deformation for fluids, and rate of deformation could be in terms of normal and shear strain rate, and we also discussed about the rate of rotation, and introduced the velocity gradient tensor analogous to the displacement gradient tensor for solids, and then we related strain rate to the velocity gradient, and then finally expressed the velocity gradient tensor as sum of strain rate tensor and rotation rate tensor, which we call as decomposition of fluid motion. Okay. Now, what we will do is all were a lot of analytical expressions, derivatives and so on. So, we look at applications or examples where we evaluate them, interpret them physically. Okay. That is the objective. Okay. So, let us take the first example. So, let us take this example on planar cuvette flow, which is well known to us. We have two plates and the top plate is moving at a velocity of Vp. So, planar cuvette flow in the narrow gap between large parallel plates is shown. The velocity field in the narrow gap is given by Vx is equal to Vp by h into y. Vp is the velocity of the plate and h is the vertical distance between the two plates. We are given the velocity of the plate as 4 millimeter per second and the height to be 4 millimeter. Okay. By numerically giving the same value, it simplifies some calculations. So, something like two plates and then the top plate is in motion, which is two plates like this, and then the top plate moves at a constant velocity. So, now at time t equal to 0, line segments AC and BD are marked in the fluid to form a cross as shown. So, we are going to track these lines, okay, and that is what is shown here. AC is the horizontal line and BD is the vertical line. And evaluate the positions of the marked points at t equal to 1.5 seconds and sketch for comparison. So, how will the position of A, B, C, D look like after 1.5 seconds? And we are also asked to calculate the rate of angular deformation and the rate of rotation of a fluid particle in this velocity field, and then comment on your results. So, now the coordinates of A, B, C, D are given. A is 1, 2, okay, and C, the end of the horizontal line is 3, 2, okay. Same y coordinate and differing in x coordinate, and compare for the vertical line BD, the coordinates are 2, 3 and 2, 1. Of course, x coordinate is same and differing in the y coordinate. And so, what you should imagine is as if you have a colored die and then marking this line at time t equal to 0, okay. And this velocity profile is linear, and that velocity profile is shown here, varying from 0 at the bottom plate to the to velocity of Vp at the top plate. Now, we are asked to find out coordinates after 1.5 seconds. Okay. So, let us do that. The velocity, how do you find coordinate? The original coordinate plus the displacement which has happened during the time 1.5 second, that is all we will have to do. Okay. So, in this case there is only the x component of velocity, there is no y component of velocity, okay. And let us take at a point A 1, 2, what will be the velocity? If we substitute Vp as 4 and h as 4 and y for this location is 2 and gives you 2 millimeter per second. Okay. That is why I said taking numerically Vp and h as equal gives us the velocity at a point as numerically equal to the y coordinate. Okay. So, if you look at this 4 points, the velocity depends only on the y coordinate. Not alone that, because of this particular example numerical value is chosen, the velocity is same as the y coordinate. So, you can quickly get to know the velocity from the coordinates. So, point A moves, remember, horizontally at a velocity of 2 millimeter per second. Point C also moves at the same velocity 2 millimeter per second, because they are the same y coordinate. But if you compare B and D, B moves at 3 millimeter per second, which is at a higher velocity, of course, because it is closer to the plate which is moving, and if you look at D is moving at 1 millimeter per second, which is closer to the stationary plate. Okay. So, now Vx is numerically equal to y coordinate, that will be easier to understand as we go along. Okay. So, now as I said, we will have to find out the displacement of point A in 1.5 second is the velocity into the time. So, 3 millimeter is the displacement, and that displacement happens in the x direction. Okay. Okay. So, after 1.5 second, what are the coordinates of point A, which we call as A dash. So, how do you calculate the original x coordinate plus the displacement, which is the velocity into the time interval, and remember there is no change in y coordinate, only if there is a vertical component, the velocity component along the y direction, that will change, but we do not have that. Okay. So, 1 plus 3 comma 2 gives you 4 comma 2. So, the new coordinate of A dash is 4 comma 2. Okay. Now, let us repeat this for the other points. B is 2 comma 3. Now, of course, now the velocity is 3 millimeter per second, as we have seen the velocity is numerically equal to the y coordinate. So, the old x coordinate plus the velocity in the x direction multiplied by the time interval, y coordinate is same. So, gives you 2 plus 4.5 comma 3 gives you 6.5 comma 3, that is the new coordinate of B, which we call as B dash. Now, similarly we can find out the other coordinates. For example, C is C dash. So, for C the old coordinate is 3, the velocity is 2 and multiply by 1.5. So, get 3 plus 3, and so the new x coordinate is 6, y coordinate is 2. Okay. Similarly, for the point D, 2 comma 1, 2 plus the velocity is just 1, time span is 1.5. So, 2 plus 1.5 gives you 3.5 and the y coordinate is 1. So, this is how the lines look at t equal to 1.5 seconds. So, this top figure shows the two lines at time t equal to 0, and the lines have become as shown in the diagram below. The line AC has become A dash C dash and the line BD has become B dash D dash. Okay. So, these are the new coordinates. A12 has become A dash 4 comma 2, similarly other coordinates as well. Okay. Now, let us run this animation, which will show you how these lines move as a function of time. Okay. This is after a particular time interval of 1.5 seconds. What we will see is how this initial the cross two lines are crossing each other, how they move as the time progresses. Okay. Okay. So, this is how they move, and what, of course, this is qualitatively shown here, and what you see here is the position of the lines at time t equal to 1.5 seconds, but as if you want to track from 0 to 1.5 seconds, this is how the line moves, okay. Both the lines move. Okay. We introduced a few tensors and with physical significance. So, we will calculate those tensors and also find out the rate of angular deformation, rate of rotation, which is asked in the question. Okay. Okay. So, now okay, let it be running. Let us go ahead with the calculation. So, velocity field is given by V x is equal to V p by h into y. Now, let us calculate the strain rate tensor for this particular velocity field. Okay. So far we have been working in terms of the expression for the strain rate tensor, but now because we are given the velocity field, we can evaluate the strain rate tensor. So, V dou V x by dou x of course is 0, V x does not depend on x, and V y itself is 0. So, dou V y by dou y anyway 0. Coming to the, remember this is these two terms put together are the shear strain rate, and divide by 2 gives you, if you divide by 2 gives you epsilon dot x y which is one component of the strain rate tensor. So, now in this component V y is 0. So, this term does not contribute. We have V x, if you partial differentiate you have V p by h and a half. So, the remember the strain rate is V p by h, but that component of the strain rate tensor is half of that, okay. And of course, we know it is symmetric. So, this term is also half V p by h, and of course, we already discussed that the diagonal components are 0. So, if you calculate the rate of angular deformation, remember rate of angular deformation is gamma dot x y epsilon dot x y is gamma dot x y by 2. When we say rate of angular deformation, it represents only these two terms. Of course, this is 0 as we have discussed. Second term is just partial derivative with respect to y, V p by h. In this case, numeric, if you substitute the numerical values, you get 1 second inverse. Okay. How do you interpret this? What is the meaning of this? Okay. Now, remember we had gamma, okay. We had gamma x y is equal to alpha plus beta based on this diagram which I have seen earlier. Okay. Now, gamma dot x y, remember it is just taking time derivative. So, if you want to write formally, it is d by dt of alpha plus beta. So, this tells you that 1 per second, that rate of angular deformation tells you that rate at which these two angles alpha plus beta together are changing. That is the significance of 1 second inverse. I will repeat it. Gamma x y is just shear strain alpha plus beta, gamma dot x y is the material derivative of that which is following the fluid motion. So, in this case the angles are alpha and beta, and we are looking at the sum of this and how that sum of that angle changes with respect to time. So, in this case the sum is positive, which means that alpha and beta are increasing, which means that the angle between, let us say at time t equal to 0 you marked these lines, and some time little later the angle would have decreased. Okay. So, rate of angular deformation tells you about rate at which alpha plus beta are changing, and if it is positive tells you that the two line segments, let us say initially they were p q and p r, now it is p star q star and p star r star, they are approaching towards each other. Okay. We already seen that earlier, remember shear strain is positive means acute angle. In this case we cannot talk about angle, remember we can always talk only about the rate at which the angle changes. So, it tells you 1 per second tells you rate at which the two line segments approach each other towards each other. Okay. Okay. Now, let us calculate the rate of rotation tensor. This anti-symmetric, okay. Strain rate tensor was symmetric. Now, rate of rotation tensor diagonal components are 0, okay. And the off diagonal components we have already seen how to kind of remember that. Remember this term is omega dot x y and this term is minus omega dot x y, and we know how to remember omega dot x y, same expression as this with the negative sign, same expression as epsilon dot xy with the negative sign, and of course because it is antisymmetric, this term is negative of this term, okay, negative of this term. Now, if you evaluate this V y is 0, we differentiate V x with respect to y, and then minus and minus sign becomes positive. So, you get half V p by h, and of course this term is minus half V p by h because they are of opposite sign, can also obtain by substituting here. Now, let us find out the rate of rotation. Rate of rotation is omega dot x y is given by this expression. Remember, rate of rotation has that half in it. Rate of angular deformation does not have half in it, only epsilon dot x y has half in it. This can be a little confusing to begin with, but please note that this relationship between epsilon dot x y and gamma dot x y. Okay, so, now if you evaluate this, which I already done, which is this term half and then 0 minus V p by h, substitute the numerical values, you get minus 0.5 second inverse. So, what does this tell you? Remember, when we introduced omega x y, we introduced that as alpha minus beta. We said alpha is counterclockwise, beta is clockwise rotation. So, we attached a sign to that because rotation takes about the sense of rotation. Now, if you want to calculate omega dot x y, then it is d by dt, the material derivative of alpha minus beta. So, now this tells you what is the net rotation. So, this rate of rotation tells you rate at which alpha minus beta changes. So, it tells about the net rate of rotation of the element, and in this case it is negative, which means it is rotating in the clockwise direction. Okay. Remember, in both the cases, at every instant we are taking two perpendicular line. At let us say t equal to 0 from t and then to t equal to 0.1, you take two perpendicular lines and they approach each other as given by the rate of angular deformation. Similarly, at next instant you cannot start with those lines which have come together. Once again start with lines which are perpendicular to each other, because always we are talking about gamma dot x y, which represents rate of angular deformation for lines which are along x and y axis. So, every instant you are always considering two perpendicular lines and what is happening to the angle between them, that is what we have seen, rate at which they come together. So, just want to mention that, for example, you start with these two lines, after some time let us say it becomes like this, it does not talk about these two lines later on. Once again it talks about only the angle change between two perpendicular lines, how they approach each other. Okay. Similarly, here also you always talk about two perpendicular lines and the rate at which alpha minus beta changes. That is why we always talk about omega dot x y, the average rate at which the element rotates, given defined by two perpendicular lines. Okay. So far we have been looking at analytical expressions. This example gives us a chance to understand the values numerically. Okay. And also like to mention that what you see here, thus the fluid flows, you have marked two lines, and then remember the fluid is continuously flowing, and these two marked lines are also let us say they are flowing along the fluid, but what you see is a representation of all the effects put together. What is that? Normal strain rate, of course it is 0 in this particular case, and so it is a combined representation of normal strain rate, shear strain rate and rotation rate. What you see is a combined effect, you do not see individual effects there, because we calculated them using the velocity field. Something equivalent to calculating use the velocity gradient tensor, not using strain rate tensor or the rotation rate tensor. What you have calculated is equivalent to calculating using the velocity gradient tensor. Hence, what you see is a representation of all the rate of deformation and the rate of rotation. Okay, that should be kept in mind.